Imagine a cosmic lion, its eyes blazing with the heat of a dying star, its mane a swirling storm of ionized gas and dust, all sculpted by the final breaths of a star that once shone like our sun. This is NGC 2392, the Lion Nebula, captured in stunning detail by NASA's James Webb Space Telescope. The eerie, face-like bubble at its heart isn't a trick of light, it's a stellar corpse, its remnants shaping the nebula's hauntingly familiar form. The mane around it isn't just random debris, it's a vast, intricate web of material ejected over millennia, glowing in the ultraviolet light of the central star's fading ember. What looks like a majestic predator is actually a cosmic graveyard, where the last gasps of a star birth a spectacle of light and shadow. Webb's instruments, NIRCam and MIRI, have revealed this alien portrait with unprecedented clarity, turning a distant death into a story of beauty and transformation. This isn't just a nebula, it's a celestial portrait of stellar evolution, frozen in time. Imagine a cosmic lion, its face etched in ionized gas and dust, its mane swirling with the remnants of a dying star. This is the Lion Nebula, formerly known as NGC 2392, captured in stunning detail by NASA's James Webb Space Telescope. What makes this discovery so remarkable is not just the breathtaking imagery, but the insight it offers into the final chapter of a star's life. The nebula's striking lion-like shape, its glowing eye, snarling mouth, and flowing mane, is not a random accident of cosmic chance. It is the result of a star's dramatic transformation, a process that has fascinated astronomers for decades. Today, the Webb telescope has revealed this structure in ways never before possible, shedding light on the intricate dance of gas, dust, and stellar remnants that shape the universe. Let's explore how this celestial lion came to be and what it tells us about the life cycles of stars. Planetary nebulae, like the Lion Nebula, are among the most beautiful and enigmatic objects in the cosmos. They are not planets, as their name suggests, but the glowing remnants of stars that have reached the end of their lives. These stars, typically around the size of our Sun, have exhausted their nuclear fuel and begin to shed their outer layers into space. What remains is a dense, hot core, the remnant of the star's once bright heart, now known as a white dwarf. This white dwarf, no larger than Earth but incredibly dense, radiates intense ultraviolet light, which ionizes the surrounding gas and dust, causing it to glow in vibrant hues of blue, green, and red. The result is a planetary nebula, a luminous shell of gas expanding outward, shaped by the star's final acts. The Lion Nebula is a prime example of this process. Its central star, now a white dwarf, is responsible for the nebula's intricate structure. The lion's face, its glowing eye, snarling mouth, and the subtle contours of its features is formed by the way the gas and dust have been sculpted by the star's intense radiation and stellar winds. These forces push the material outward, creating complex patterns that can resemble animals, objects, or even abstract shapes. In the case of the Lion Nebula, the alignment of gas clouds and the geometry of the star's outflow have given rise to the unmistakable silhouette of a lion. The mane of the nebula, a halo of ionized gas surrounding the face, is the result of material being ejected in all directions, creating a diffuse, glowing halo that stretches across the image. What makes the Webb telescope's view of the Lion Nebula so groundbreaking is the unprecedented clarity it provides. Previous observations, using visible light telescopes, could only hint at the nebula's structure. The Webb telescope, with its advanced near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, has captured details that were previously hidden. These instruments are designed to detect light at wavelengths that pass through the Earth's atmosphere, allowing astronomers to peer deeper into the cosmos than ever before. The NIRCam reveals the glowing gas and dust in intricate detail, while MIRI captures the faint, warm glow of the nebula's outer regions. Together, they paint a picture of the Lion Nebula that is both scientifically rich and visually stunning. The lion's face, for instance, is not a static feature. It is a dynamic structure shaped by the interplay of forces over thousands of years. The central white dwarf emits intense ultraviolet radiation, which ionizes the surrounding gas, causing it to emit light. This process is not uniform. Variations in the density of the gas and the direction of the star's outflow create subtle differences in brightness and color. The lion's eye, for example, appears brighter than the rest of the face, suggesting that the gas in that region is denser or more concentrated. Similarly, the snarling mouth and the contours of the face are the result of the star's outflow interacting with surrounding material, creating shadows and highlights that give the nebula its lifelike appearance. The Lion Nebula's structure also provides clues about the star's history. The way the gas and dust are distributed suggests that the star has been shedding its outer layers for thousands of years. This process, known as a stellar wind, is a gradual release of material that can take place over tens of thousands of years. As the star ages, its outer layers become increasingly unstable, leading to periodic bursts of material being ejected. These bursts can create the complex, asymmetric shape seen in many planetary nebulae. The Lion Nebula's lion-like form may be the result of such a series of eruptions, each shaping the nebula's structure in a unique way. Beyond its aesthetic appeal, the Lion Nebula is a critical subject for astrophysical study. Planetary nebulae are important laboratories for understanding the life cycles of stars. They provide insights into how stars evolve, how they shed their outer layers, and how their remnants contribute to the chemical enrichment of the universe. The gas and dust expelled by these stars eventually form new stars and planetary systems, making planetary nebulae vital to the cycle of stellar evolution. By studying the Lion Nebula, astronomers can learn more about the physical processes that govern these transformations and how they shape the cosmos. The Webb telescope's ability to capture such detailed images of the Lion Nebula is a testament to the power of modern astronomy. Before Webb, observations of planetary nebulae were limited by the Earth's atmosphere, which blocks much of the infrared light emitted by these objects. The James Webb Space Telescope, positioned in orbit beyond the Earth's atmosphere, can detect this infrared light without interference, revealing structures and details that were previously invisible. This capability has allowed astronomers to study planetary nebulae in ways that were once thought impossible, opening new avenues for research and discovery. The Lion Nebula's discovery also highlights the importance of long-term observational campaigns in astronomy. While the Webb telescope's images are stunning, they are the result of years of planning, engineering, and scientific collaboration. The telescope's instruments were designed with the specific goal of studying distant, faint objects, and the Lion Nebula is a perfect example of how these capabilities can unlock new knowledge. By combining data from multiple instruments and analyzing the nebula's structure over time, astronomers can build a more complete picture of its evolution and the processes that shape it. As we look at the Lion Nebula, we are not just observing a beautiful cosmic phenomenon. We are witnessing the final act of a star's life, a dramatic transformation that has shaped the universe for billions of years. The lion's face, carved by the star's radiation and outflow, is a reminder of the dynamic and ever-changing nature of the cosmos. Each planetary nebula is a unique snapshot of a star's final moments, a fleeting moment in the vast timeline of stellar evolution. The Lion Nebula, with its striking form and intricate details, stands as a testament to the power of observation and the enduring mystery of the universe. Through the James Webb Space Telescope, we have taken a step closer to understanding the life and death of stars, and in doing so, we have glimpsed the beauty of the cosmos in ways never before imagined. NASA's James Webb Space Telescope imaged the planetary nebula NGC 2392, the Lion Nebula, using the observatory's NIRCam and MIRI instruments. The central star's remains are responsible for the nebula's structure, including a lion face-shaped bubble of ionized gas and dust mane. This part of our deep dive into Lion Nebula Roars and websites focuses on, walk through how scientists found or confirmed this instruments, telescopes, missions, method, timeline. Make the process itself feel impressive. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The Lion Nebula, or NGC 2392, is more than just a striking cosmic image, it's a window into the final chapter of a star's life. To understand its significance, we must first step back and consider the life cycle of a star. Like our sun, stars spend billions of years fusing hydrogen into helium in their cores, but when they exhaust their nuclear fuel, their fate is sealed. For stars similar to the Sun, this moment arrives when they shed their outer layers, creating a glowing shell of ionized gas and dust. This shell, illuminated by the leftover core of the star, now a dense, Earth-sized white dwarf, is what we call a planetary nebula. Despite the name, these objects have nothing to do with planets. They're the final, luminous phase of a star's existence, a cosmic spectacle of light and matter. The Lion Nebula is one such example. Its eerie, lion-like face a testament to the intricate dance of physics that shapes these celestial phenomena. At the heart of the Lion Nebula lies a white dwarf, the remnant of the star that once dominated this region of space. This dense, Earth-sized ember of a star is no longer undergoing fusion, but its intense gravitational pull and residual heat still exert a profound influence. The white dwarf's radiation is the key to the nebula's luminosity. As the ejected material, gas and dust expelled during the star's final stages, interacts with this radiation, it becomes ionized, glowing in vibrant hues of blue, green, and red. These colors are not random, they are the fingerprints of the elements present. Oxygen, sulfur, and nitrogen, products of stellar fusion, emit light at specific wavelengths, creating the nebula's striking palette. The Lion Nebula's colors, therefore, are a direct reflection of the star's composition and the processes that shaped it. But what makes the Lion Nebula's structure so remarkable? The nebula's lion face is not a coincidence, it is the result of complex interactions between the star's remnants and the surrounding interstellar medium. The central white dwarf's radiation heats and ionizes the ejected material, but the nebula's shape is also influenced by the star's own history. As the star shed its outer layers, it did so in a way that created a symmetrical, almost sculpted pattern. This symmetry suggests that the star's final moments were marked by a steady, controlled ejection of material, rather than a chaotic explosion. The lion face, with its distinct features, is a snapshot of this process, a moment frozen in time. The mane of the nebula, a dense, filamentary structure surrounding the face, is likely composed of denser clumps of gas and dust that have been shaped by the star's winds or magnetic fields. These structures are not static, they are dynamic, evolving as the nebula interacts with the surrounding space over millions of years. The Lion Nebula's significance lies in its ability to reveal the underlying physics of stellar evolution. Planetary nebulae are not just beautiful, they are crucial to the life cycle of stars and the chemical enrichment of the universe. When a star like the Sun dies, it does not simply vanish, it disperses its outer layers into space, scattering elements heavier than helium into the interstellar medium. These elements, forged in the star's core through nuclear fusion, become the building blocks for new stars, planets, and even life. The Lion Nebula is a vivid reminder of this cosmic recycling. Every glowing filament and ionized gas cloud is a repository of elements that will one day contribute to the formation of new celestial bodies. By studying such nebulae, astronomers can trace the distribution of elements across the galaxy and gain insights into the processes that govern stellar death and rebirth. Moreover, the Lion Nebula's structure provides clues about the mechanisms that shape planetary nebulae. While many planetary nebulae exhibit symmetrical or complex shapes, the Lion Nebula's lion face is particularly striking. This suggests that the star's final moments were influenced by specific physical conditions. One possibility is that the star's magnetic field played a role in directing the flow of ejected material, creating the intricate patterns observed. Another theory involves binary star systems, where a companion star might have interacted with the dying star, influencing the ejection of material and the resulting shape. However, the Lion Nebula's structure appears to be the result of a single star's evolution, indicating that even solitary stars can create complex, beautiful structures through their own internal dynamics. The study of such nebulae helps scientists refine models of stellar evolution, offering a deeper understanding of how stars transition from their main sequence lives to their final, luminous demise. The James Webb Space Telescope's ability to capture the Lion Nebula in such detail is a testament to the power of modern astronomy. Unlike earlier telescopes, which struggled to resolve the fine structures of planetary nebulae, Webb's advanced instruments, particularly the NIRCam and MIRI, allow astronomers to peer into the nebula's depths with unprecedented clarity. These instruments operate in the infrared spectrum, enabling them to detect the faint glow of ionized gas and dust that might otherwise be obscured by interstellar dust. The resulting images reveal not just the nebula's overall structure but also subtle details, such as the distribution of different elements and the dynamics of gas flow. For example, the Lion face's glowing contours are not uniform, they vary in intensity and color, indicating differences in temperature, density, and composition across the nebula. These variations provide critical data for understanding the physical processes at play, from the star's radiation to the interstellar medium's influence. The Lion Nebula's significance extends beyond its immediate beauty. It serves as a laboratory for studying the physics of ionized gas and the behavior of magnetic fields in space. The ionized gas in planetary nebulae is a plasma, a state of matter where electrons are stripped from atoms, creating a highly conductive medium. The interaction between this plasma and the magnetic fields of the central white dwarf can generate complex patterns, such as the filamentary structures observed in the nebula's mane. These structures are not static, they are dynamic, with gas flowing and colliding in ways that can be modeled using astrophysical simulations. By analyzing the Lion Nebula's features, scientists can test these models and refine their understanding of how magnetic fields and plasma dynamics shape the universe. Such studies have broader implications, as similar processes occur in other astrophysical environments, from the solar wind to the magnetized clouds of interstellar space. Finally, the Lion Nebula reminds us of the transient nature of stars and the cyclical nature of the cosmos. While the nebula's glowing face is a striking image, it is also a fleeting moment in the life of a star. The white dwarf at its center will eventually cool and fade, becoming a black dwarf, a cold, dark remnant that will persist for billions of years. Yet, even in this final phase, the star's legacy endures. The elements it dispersed will continue to shape the universe, contributing to the formation of new stars and planetary systems. The Lion Nebula, therefore, is more than a cosmic curiosity, it is a symbol of the interconnectedness of all matter in the universe. Each glowing filament and ionized cloud is a thread in the cosmic tapestry, a reminder that the life and death of stars are not isolated events but integral parts of a grand, ongoing process. In the end, the Lion Nebula's story is one of transformation, from the birth of a star to its final, luminous demise. It is a testament to the power of physics to shape the universe and the enduring curiosity of scientists to unravel its mysteries. By studying such nebulae, we gain not only a deeper understanding of stellar evolution but also a greater appreciation for the intricate, beautiful processes that govern the cosmos. The Lion Nebula, with its lion face and glowing mane, is a reminder that even in the final stages of a star's life, there is still wonder to be found, a reminder that the universe is both vast and full of meaning. For millennia, humans have gazed at the night sky, captivated by the glowing clouds of light that drift across the cosmos. These celestial objects, now known as planetary nebulae, have fascinated astronomers for centuries. But our understanding of them has evolved dramatically over time, shaped by technological advancements and scientific curiosity. The Lion Nebula, imaged in stunning detail by the James Webb Space Telescope, is a testament to this journey, a story that begins with ancient observations and culminates in the precision of modern infrared astronomy. Let's explore how our perception of these cosmic phenomena has transformed, from the earliest glimpses of their glow to the groundbreaking revelations made possible by today's most powerful telescope. Long before the advent of telescopes, planetary nebulae were observed as faint, glowing patches of light in the night sky. Ancient civilizations, such as the Chinese and Greeks, noted these objects, though they often misidentified them as nebulous clouds or even distant planets. The term planetary nebula itself is a misnomer, coined in the 18th century by William Herschel, who mistakenly believed these objects resembled the planet Saturn. Despite this confusion, early astronomers recognized their unique appearance, bright, round, and often surrounded by faint halos. However, without the tools to peer deeper, their true nature remained elusive. The 19th century marked a turning point in the study of planetary nebulae. With the development of larger telescopes, such as the 19th century NIRCam Observatory's 40-inch refractor, astronomers began to resolve these nebulous shapes into their intricate structures. One of the most significant breakthroughs came in 1864, when the British astronomer William Huggins used spectroscopy to analyze the light from the Orion Nebula. His findings revealed that planetary nebulae were not clouds of gas but instead glowing shells of ionized material surrounding dying stars. This discovery laid the foundation for modern astrophysics, revealing that these objects were the final stages of stellar evolution. In the 20th century, the study of planetary nebulae accelerated with the advent of radio astronomy and space-based observatories. The 1950s and 1960s saw the development of spectroscopic techniques that allowed astronomers to determine the chemical composition of these nebulae. These studies confirmed that planetary nebulae were rich in elements like carbon, nitrogen, and oxygen, products of nuclear fusion in their parent stars. Meanwhile, the launch of the Hubble Space Telescope in 1990 revolutionized our view of these objects. For the first time, astronomers could capture high-resolution images of planetary nebulae, revealing their complex structures and dynamic processes. Hubble's iconic image of the pillars of creation in the Eagle Nebula, for example, showcased the intricate interplay of gas, dust, and star formation, but it was the broader field of planetary nebulae that truly benefited from Hubble's capabilities. The Hubble Space Telescope's contributions to planetary nebulae research were profound. Its ability to capture detailed images in visible light allowed astronomers to study the shapes, sizes, and kinematics of these objects. One of the most striking examples is the Cat's Eye Nebula, a planetary nebula that Hubble imaged in exquisite detail, revealing concentric shells and intricate filaments. These observations hinted at the complex physics at play in these objects, including the interaction between the stellar wind and the surrounding interstellar medium. However, despite Hubble's achievements, there were limitations. Many planetary nebulae emit most of their light in the infrared spectrum, a range of wavelengths that Hubble could not fully explore. This gap in our understanding spurred the development of new telescopes capable of peering deeper into the cosmos. Enter the James Webb Space Telescope, launched in 2021. Designed to observe the universe in the infrared, Webb's instruments are uniquely suited to studying planetary nebulae. Unlike Hubble, which primarily operates in the visible and ultraviolet ranges, Webb's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, can detect the faint, redshifted light emitted by these objects. This capability has opened a new window into the study of planetary nebulae, allowing astronomers to peer through the dusty veils that obscure their central stars. The Lion Nebula, NGC 2392, is a prime example of this transformative power. Earlier observations, including those from Hubble, had hinted at its complex structure, but it was only with Webb's infrared vision that the full majesty of the Lion Nebula's mane and face became apparent. The Lion Nebula itself is a striking example of the beauty and complexity of planetary nebulae. Located approximately 4,000 light-years from Earth, this object is the remnant of a star that has reached the end of its life. As the star exhausted its nuclear fuel, it shed its outer layers, creating a glowing shell of ionized gas and dust. The central star, now a white dwarf, emits intense ultraviolet radiation that ionizes the surrounding material, causing it to glow in hues of blue and green. The nebula's distinctive shape, a lion's face with a mane of filaments, was only fully revealed by Webb's infrared imaging. This structure is not random, it is the result of the star's complex interactions with its environment, including the ejection of material in specific directions and the influence of magnetic fields. The significance of the Lion Nebula's image extends beyond its aesthetic appeal. It represents a milestone in our understanding of stellar evolution and the life cycles of stars. Planetary nebulae are crucial for the chemical enrichment of the universe, as they disperse elements like carbon and oxygen into space, which later contribute to the formation of new stars and planets. The Lion Nebula's intricate structure also provides clues about the processes that shape these objects. For instance, the lion's face, a bubble of ionized gas, suggests that the central star's radiation has sculpted the surrounding material into a specific form. Meanwhile, the mane of filaments indicates the presence of complex dynamics, such as the interaction between the stellar wind and the interstellar medium. The journey to understand planetary nebulae like the Lion Nebula is a testament to humanity's relentless pursuit of knowledge. From the earliest observations of glowing patches in the night sky to the high-resolution images captured by Hubble and Webb, each step has deepened our understanding of these cosmic phenomena. The Lion Nebula's image, with its striking lion face and intricate mane, is not just a visual marvel but a scientific breakthrough. It highlights the power of infrared astronomy to reveal the hidden structures of the universe and underscores the importance of continued exploration. As we look to the future, the data gathered by Webb and other observatories will undoubtedly lead to new discoveries, further expanding our knowledge of the cosmos and the life cycles of stars. The Lion Nebula, with its striking lion face and mane of ionized gas and dust, has captivated astronomers since its first detailed imaging by the James Webb Space Telescope. Yet, despite the remarkable clarity of these images, the nebula's origins and evolution remain shrouded in mystery. Scientists are still grappling with fundamental questions about how such intricate structures form, what forces shape them, and how they fit into the broader story of stellar life cycles. While the central star's remains are clearly the driving force behind the nebula's structure, the exact mechanisms that gave rise to its unique shape, particularly the lion's face, remain a subject of intense debate. Researchers are still piecing together the complex interplay of stellar winds, magnetic fields, and cosmic radiation that may have sculpted this celestial masterpiece. But what exactly caused the nebula's distinctive features? Is the lion's face a coincidence, or does it hint at deeper physical processes at work? These questions underscore the fact that even with the most advanced telescopes, the universe still holds secrets that challenge our understanding of astrophysics. The Lion Nebula's enigmatic nature is not a flaw in our knowledge, but rather a testament to the complexity of the cosmos and the enduring curiosity that drives scientific inquiry. As we delve deeper into the mysteries of this planetary nebula, we uncover not just the story of a single star's death, but also the broader implications for how stars shape their surroundings and leave behind their final cosmic legacies. One of the most pressing questions revolves around the nebula's structure itself. The lion face and mane are not random formations, they are the result of a delicate balance between the star's ejected material and the surrounding interstellar medium. Yet, the exact processes that led to this specific configuration are still debated. Some scientists argue that the nebula's shape is a direct consequence of the central star's pulsations, which may have created shockwaves that compressed and sculpted the surrounding gas. Others suggest that magnetic fields played a crucial role, guiding the outflow of material into the distinctive patterns observed. But how do these theories hold up under scrutiny? The answer may lie in the nebula's composition and dynamics. By analyzing the distribution of ionized gas and dust, researchers can trace the history of the star's mass loss and the forces that shaped the nebula. However, the data from the James Webb Space Telescope has revealed complexities that challenge existing models. For instance, the nebula's structure appears to be more intricate than previously thought, with subtle variations in density and temperature that suggest a more dynamic interaction between the star and its environment. These findings raise new questions. Could the nebula's shape be influenced by multiple factors, rather than a single mechanism? Or is there an underlying pattern that we have yet to decipher? The debate over the nebula's formation highlights the broader challenge of understanding planetary nebulae in general. While many of these objects exhibit similar characteristics, such as a central star surrounded by a glowing shell of gas, each nebula is unique in its structure and complexity. The Lion Nebula's lion face, for example, is far more elaborate than the symmetrical shapes often seen in other planetary nebulae. This raises the question of whether there are fundamental differences in how different stars create their nebulae, or if the lion's face is simply an extreme example of a more common phenomenon. Scientists are also exploring whether the nebula's shape could be influenced by external factors, such as the gravitational pull of nearby stars or the presence of interstellar clouds. However, these possibilities remain speculative, as the nebula's location in the constellation Lyra suggests it is relatively isolated from other massive objects. This isolation makes it an ideal candidate for studying the intrinsic processes of planetary nebulae, yet it also means that the answers to its mysteries may lie within the nebula itself rather than its surroundings. Another layer of complexity arises from the nebula's central star. While we know that the star's remains are responsible for the nebula's structure, the exact state of the star remains uncertain. Is it a white dwarf, the remnant of a once vast star that has shed its outer layers? Or could it be a different type of stellar remnant, such as a neutron star or even a black hole? The James Webb Space Telescope's observations have provided valuable insights into the star's properties, but many details remain elusive. For instance, the star's temperature, luminosity, and magnetic field strength are all factors that could influence the nebula's appearance. However, without more detailed measurements, scientists are left to infer these properties based on indirect evidence. This uncertainty has sparked debates about the star's evolutionary history. Could it have undergone multiple phases of mass loss before forming the nebula, or is the lion face a direct result of a single, dramatic event? These questions are not just academic, they have profound implications for our understanding of stellar evolution. If the central star's properties are different from what we currently assume, it could mean that our models of how stars transition from red giants to planetary nebulae are incomplete. The Lion Nebula, therefore, serves as a critical test case for refining these models. Yet, even with the wealth of data provided by the James Webb Space Telescope, there are still gaps in our knowledge. For example, the nebula's ionized gas and dust may contain elements that were not previously detected in other planetary nebulae. These elements could provide clues about the star's composition and the processes that occurred during its final stages of life. However, identifying these elements requires advanced spectroscopic analysis, which is still an ongoing effort. The nebula's structure also raises questions about the role of cosmic radiation in shaping planetary nebulae. While ultraviolet radiation from the central star is known to ionize the surrounding gas, the exact contribution of other sources such as cosmic rays or nearby supernova remnants remains unclear. Some researchers suggest that these external influences could have played a role in sculpting the nebula's intricate features, but without direct evidence, this remains a hypothesis. The interplay between the central star and its environment is a delicate balance, and the Lion Nebula's complexity suggests that this balance may have been more dynamic than previously thought. However, the nebula's age also presents a puzzle. While planetary nebulae typically have lifespans of a few thousand years, the Lion Nebula's structure suggests that it may be in a transitional phase. This raises the question of whether the nebula is still evolving or if it has already reached a stable state. If the nebula is still in the process of expanding, its future shape could be influenced by factors such as the density of the surrounding interstellar medium or the presence of other nearby stars. These uncertainties highlight the importance of long-term observational studies, as the nebula's evolution may take place over timescales that are difficult to observe with current technology. The Lion Nebula's mysteries are not limited to its structure and composition, they also extend to its place in the broader context of stellar evolution. Planetary nebulae are the final stages of certain stars' lives, but the exact mechanisms that lead to their formation are still not fully understood. While we know that stars like our Sun will eventually shed their outer layers to form planetary nebulae, the specific processes that shape these objects vary widely. The Lion Nebula's unique features may represent an extreme example of this variability, but they could also challenge existing theories about how stars interact with their surroundings. For instance, the nebula's lion face may indicate a more complex interaction between the star and its environment than previously assumed. This could mean that factors such as magnetic fields, stellar winds, or even the star's rotation play a more significant role in shaping planetary nebulae than previously thought. However, these ideas are still being tested, and the data from the James Webb Space Telescope has provided new insights that may help refine these theories. The nebula's complexity also raises questions about the role of turbulence and instabilities in the surrounding gas. While some planetary nebulae exhibit smooth, symmetrical shapes, others, like the Lion Nebula, have more chaotic and intricate structures. This suggests that the processes that shape these objects may be more dynamic and unpredictable than previously believed. Understanding these dynamics is crucial for developing a comprehensive model of how stars evolve and how their remnants interact with the cosmos. However, the Lion Nebula's enigmatic nature also serves as a reminder of the vast unknowns that still exist in astrophysics. Despite the advances made possible by instruments like the James Webb Space Telescope, there are still many aspects of planetary nebulae that remain unexplained. For example, the exact mechanisms that lead to the formation of complex structures like the lion face are not yet fully understood. Additionally, the role of dark matter or other exotic phenomena in shaping these objects is still a topic of speculation. While these ideas may seem far-fetched, they underscore the fact that our understanding of the universe is constantly evolving. The Lion Nebula, with its striking appearance and intricate details, serves as a powerful reminder of the beauty and complexity of the cosmos. It is a testament to the enduring mystery of the universe and the relentless pursuit of knowledge that drives scientific exploration. As researchers continue to study the nebula's structure, composition, and dynamics, they are not just uncovering the story of a single star's death, they are also shedding light on the broader processes that shape the universe. The Lion Nebula's mysteries may never be fully resolved, but each new discovery brings us closer to understanding the intricate dance of forces that govern the cosmos. In the end, the nebula's enigmatic nature is not a limitation, but an invitation to continue exploring the wonders of the universe. As we look beyond the stunning image of the Lion Nebula captured by the James Webb Space Telescope, the next chapter in our exploration of this cosmic phenomenon lies in the future missions and instruments that will build on this discovery. The Lion Nebula, with its intricate lion face-shaped structure and the enigmatic interplay of ionized gas and dust, offers a unique window into the late stages of stellar evolution. But to fully unravel its mysteries, we must turn our gaze to the next generation of space telescopes and observational tools that are currently in development or already in operation. These missions will not only confirm what we already know but also challenge our assumptions, revealing new layers of complexity in the story of this planetary nebula and its central star. One of the most anticipated follow-up efforts will involve the Nancy Grace Roman Space Telescope, a successor to the Hubble Space Telescope that is set to launch in the mid-2020s. While the Roman telescope's primary mission is to study dark energy and exoplanets, its advanced infrared imaging capabilities will allow astronomers to probe the Lion Nebula's structure with unprecedented precision. The telescope's wide-field camera, for instance, could capture broader contextual images of the nebula's surroundings, helping to map how it interacts with the interstellar medium. By comparing these observations to the JWST data, scientists might uncover subtle variations in the nebula's composition or detect fainter features that were previously obscured by the limitations of earlier instruments. Additionally, the Roman telescope's ability to conduct large-scale surveys of similar planetary nebulae could reveal patterns in their formation, shedding light on the universal processes that shape these glowing cosmic sculptures. Ground-based observatories will also play a critical role in extending our understanding of the Lion Nebula. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the largest optical telescope ever built, with a primary mirror spanning 39 meters. When operational, the ELT's adaptive optics technology will allow it to peer into the nebula's fainter regions with remarkable clarity, potentially resolving features that even the James Webb Space Telescope cannot fully capture. This could include detailed studies of the nebula's outer shell, where the interaction between the central star's ejected material and the surrounding interstellar environment is thought to occur. The ELT spectroscopic instruments will also enable astronomers to analyze the chemical composition of the gas and dust in the nebula, identifying elements and isotopes that may provide clues about the star's evolutionary history. For example, the presence of heavier elements like carbon or oxygen could indicate whether the star underwent processes such as binary interactions or mass loss events that are not yet fully understood. Another promising avenue for future research involves the use of spectroscopy to probe the dynamics of the Lion Nebula. While the JWST's MIRI instrument has already provided valuable insights into the nebula's structure, upcoming missions like the Spica Infrared Telescope, a Japanese-led project planned for the 2030s, could push this analysis further. Spica's ultracold detectors will be capable of capturing faint thermal emissions from the nebula's cooler regions, allowing scientists to study the distribution of molecules such as water vapor or carbon monoxide. These molecules could serve as tracers for the nebula's kinematics, revealing how the gas is moving and how it might be influencing the surrounding space. Such data would be crucial for refining models of how planetary nebulae evolve over time, particularly in relation to the central star's energy output and the role of magnetic fields in shaping the nebula's morphology. Beyond the technical capabilities of new instruments, the future of Lion Nebula research also hinges on the development of advanced computational models and data analysis techniques. The vast amount of data generated by missions like the James Webb Space Telescope requires sophisticated algorithms to extract meaningful patterns. Future missions will likely integrate machine learning and artificial intelligence to automate the detection of subtle features in the nebula's structure. For instance, these tools could help identify previously undetected filaments or asymmetries in the Lion face-shaped bubble, which might hint at complex interactions between the central star and its environment. Additionally, simulations of stellar evolution will become increasingly detailed, incorporating data from the Lion Nebula to test hypotheses about how stars shed their outer layers and form these intricate nebulae. Such simulations could even predict the nebula's future evolution, offering a glimpse into how it will change over the next few thousand years. The study of planetary nebulae like the Lion Nebula also has broader implications for understanding the life cycles of stars and their role in the universe. As we look to the future, missions such as the European Space Agency's Euclid telescope, which is designed to map the universe's dark matter and dark energy, might indirectly contribute to this field. While Euclid's primary focus is cosmological, its ability to detect faint light from distant objects could help identify other planetary nebulae in remote regions of the galaxy. These discoveries would expand our sample size, allowing scientists to compare the Lion Nebula to its counterparts and identify commonalities or anomalies in their formation processes. Such comparisons are essential for building a comprehensive picture of how stars like our Sun transition from red giants to planetary nebulae, ultimately contributing to the cosmic cycle of element creation and distribution. However, the future of Lion Nebula research is not without challenges. One of the key limitations of current and upcoming missions is their ability to observe the nebula in certain wavelengths of light. For example, while the James Webb Space Telescope excels at capturing infrared data, it cannot detect the faint radio emissions that might reveal the presence of magnetic fields or high-energy particles in the nebula. Future missions like the Square Kilometre Array, SKA, a next-generation radio telescope array under construction in Africa and Australia, could address this gap. The SKA's unparalleled sensitivity to radio waves might allow astronomers to study the nebula's magnetic environment in ways that are currently impossible, potentially uncovering new mechanisms that shape its structure. Similarly, the development of space-based observatories that operate in the far ultraviolet or X-ray ranges could provide additional insights into the nebula's high-energy processes, such as the interaction between the central star's radiation and the surrounding gas. Another exciting frontier lies in the potential for multi-wavelength observations that combine data from different instruments to create a more complete picture of the Lion Nebula. For instance, pairing JWST's infrared images with data from the Chandra X-ray Observatory could reveal how the nebula's ionized gas interacts with high-energy particles emitted by the central star. Such combined observations might also help identify regions where the nebula is influencing its surroundings, such as by triggering the formation of new stars in nearby molecular clouds. These insights would not only deepen our understanding of the Lion Nebula but also highlight the interconnectedness of cosmic phenomena, showing how the life cycle of a single star can have far-reaching effects on its galactic neighborhood. In addition to these technical advancements, the future of Lion Nebula research will also depend on the collaboration between international space agencies and scientific communities. The complexity of studying planetary nebulae requires a multidisciplinary approach, bringing together experts in astrophysics, computational modeling, and observational techniques. As new missions come online, they will likely foster partnerships that enable the sharing of data and resources, accelerating discoveries that would be impossible to achieve in isolation. For example, the upcoming James Webb Space Telescope's successor, the NASA/ESA/NASA Space Telescope, may work in tandem with ground-based observatories to conduct coordinated observations of the Lion Nebula, ensuring that no detail is overlooked. Ultimately, the study of the Lion Nebula is a testament to the power of human curiosity and the relentless pursuit of knowledge. While the James Webb Space Telescope has already provided a stunning glimpse into this cosmic masterpiece, the future holds the promise of even greater revelations. As new instruments and techniques emerge, they will not only confirm what we already know but also challenge our assumptions, revealing new layers of complexity in the story of this planetary nebula. By continuing to explore the Lion Nebula and similar objects, we take a step closer to understanding the fundamental processes that shape the universe and our place within it. In the vast tapestry of the cosmos, some celestial objects defy expectation, revealing secrets that challenge our understanding of stellar evolution. Among them is the Lion Nebula, a planetary nebula captured in stunning detail by NASA's James Webb Space Telescope. This image, rendered through Webb's NIRCam and MIRI instruments, unveils a structure so intricate it resembles the face of a lion, its ionized gas and dust forming a mane-like halo around a central star. But this isn't just a beautiful anomaly. It's a cosmic story written in light, one that illuminates the final chapter of a star's life. The Lion Nebula, officially known as NGC 2392, is a testament to the dramatic transformation stars undergo as they near the end of their existence. When a star like our Sun exhausts its nuclear fuel, it sheds its outer layers, creating a glowing shell of gas and dust. In this case, the central star's remnants sculpted the nebula's striking features, with the lion's face emerging from the intricate interplay of radiation and ejected material. What makes this discovery particularly profound is the role of Webb's advanced instruments. Unlike its predecessors, Webb's NIRCam and MIRI can peer into the infrared spectrum, revealing details hidden from optical telescopes. This allowed scientists to trace the nebula's structure with unprecedented clarity, uncovering the delicate balance between stellar winds and magnetic fields that shaped its form. The lion's mane, for instance, isn't random, it's a consequence of the star's complex interactions with its environment. Yet, the most astonishing part of this revelation lies in the nebula's scale. While the lion's face appears colossal in the image, it's actually a relatively small structure in cosmic terms, spanning just a fraction of a light-year. This underscores the immense scale of interstellar processes, where even the most dramatic phenomena are dwarfed by the vastness of space. The Lion Nebula also serves as a reminder of the fleeting beauty of stellar life cycles. Planetary nebulae are brief, lasting only a few thousand years, a blink in the universe's timeline. Yet, they leave behind luminous imprints that outlive their creators, offering glimpses into the past of stars that no longer exist. By studying such objects, astronomers piece together the life histories of stars, refining models of how they evolve and die. The Lion Nebula's image, therefore, is more than a visual marvel, it's a key to unlocking the mysteries of stellar death and rebirth. As we reflect on this cosmic portrait, it's humbling to consider the forces at play. The lion's face isn't a static sculpture but a dynamic, ever-changing structure shaped by the star's residual energy. Over time, the nebula will fade, its gases dispersing into the interstellar medium, eventually contributing to the formation of new stars. In this way, the cycle continues, a reminder that even in the emptiness of space, creation and destruction are inextricably linked. The James Webb Space Telescope's ability to capture such details isn't just a triumph of technology, it's a bridge between the observable universe and the questions that drive human curiosity. Every image like the Lion Nebula invites us to wonder, what other secrets lie hidden in the cosmic dark? What other stories are waiting to be told? For those who seek answers, the journey begins with a single question and the tools to explore it. If you've enjoyed this deep dive into the Lion Nebula, consider subscribing to FactVerse for more explorations of the universe's most enigmatic wonders. And if you have your own theories or questions about this cosmic lion, we'd love to hear them in the comments. The universe is full of mysteries, and every discovery brings us one step closer to understanding our place within it.